Let's learn about some matrix operations, specifically the sum of matrices and the scalar multiplication. Let's begin with an example. Suppose we're given the two matrices A and B that you see right here, and we wanted to add them. In order to add the matrix A and the matrix B, we simply add the corresponding entries. So for example, the entry in location 1, 1 for A is a 1, and the location 1, 1 for B is a -3. To get the entry in location 1, 1 for the sum, we simply add 1 plus -3. Similarly, we add 4 and 1, and we add -2 and 0 to get this entry right here, and so forth. Similarly, for the second row, we add 0 and 2 to find this entry. We add -3 and 7 to get this entry, and we add 5 and 1 to get this final entry. And when you do the math, we end up with this matrix right here. It's pretty clear that A and B must have the same dimensions in order for this sum to be defined. After all, we're adding corresponding entries, and if the matrices are not of the same size, then there are no corresponding entries. So for example, if A was the matrix from above, but we have a second matrix C given right here, which is only a 2 by 2 matrix, 2 rows and 2 columns, then their sum A plus C is not defined because A is a 2 by 3 matrix. It has an extra column that has nothing corresponding to it in the matrix C. More generally, if A and B are m by n matrices, then A plus B is of the same dimension. It's also an m by n matrix. So here you see two matrices A and B. Each of them has m rows and n columns. And so the sum also has m rows and n columns. In particular, the element in row I and column J, which is Aij for the A matrix and Bij for the B matrix, those two elements get added up to form the element in row I and column J in the matrix A plus B. Next, let's look at scalar multiplication. Suppose A is again this matrix right here, and we wanted to multiply this matrix by 3. What is 3 times A? In order to find 3 times A, we simply multiply each element of A by 3. So for example, this 1 here is multiplied by 3 to get 3 times 1, or this 4 is multiplied by 3 to get 3 times 4, this -2 is multiplied by 3, and so forth. In the end, we have 3 times 1 equals 3, 3 times 4 equals 12, 3 times -2 equals -6. For the second row, we have 3 times 0 is 0, 3 times -3 is -9, and 3 times 5 equals 15. Similarly, the matrix minus A, which is short for -1 times A, is obtained by multiplying each entry of A by -1. So you see all these -1s in front of all the elements of A, and so that corresponds to simply putting a negative sign in front of each element of A. So 1 becomes -1, 4 becomes -4, -2 becomes 2, 0 remains 0, -3 becomes 3, and 5 becomes -5. More generally, if lambda is a real number. By the way, if you're unhappy with using a Greek letter here, you can simply say K. But I'm going to say lambda. If lambda is a real number, then lambda times A is given by multiplying each element of A with the number lambda. So lambda times 1, lambda times 0, lambda times 4, lambda times -3, and so forth. We can even combine addition and scalar multiplication of matrices. Let again A and B be the two matrices we started with. Then A minus B is the same as the matrix A plus -1 times B. And so we take all the entries of A and we subtract from it all the entries of B. And we end up with a matrix 1 minus -3, which is 4. 4 minus 1 equals 3. -2 minus 0 is -2. 0 minus 2 is -2. -3 minus 7 is -10. 5 minus 1 equals 4. Similarly, if we wanted to find the matrix 2A plus 3B, then we would first take the matrix A and multiply each of its entries by 2, and then add to that 3 times each entry of the matrix B. And we end up with 2 times 1 plus 3 times negative 3, which equals negative 7, 2 times 4 plus 3 times 1, which is 11, 2 times negative 2 plus 3 times 0, which is negative 4, and so forth. We now can find some properties for the addition of matrices and the scalar multiplication of matrices. Namely, we use facts about addition and multiplication of real numbers, so that we can easily verify the following theorem. Matrix addition is commutative, which means it doesn't matter whether you add A plus B or B plus A, the result is the same. Matrix addition is also associative, which means if you want to add 3 matrices, it doesn't really matter which 2 you add first. You can add A and B first and then add C to the result, or you can add A to the result of adding B and C to each other. We also have a distributive property, which describes how scalar multiplication and matrix addition interact with each other. So if you wanted to multiply the sum of A and B with a number lambda, alternatively, you could multiply through and sort of use a claw law here and multiply lambda A and lambda B first and then add the results to each other. We have a second distributive law, which corresponds to adding 2 real parameters to each other and then multiplying the result with a matrix A. And again, there's a claw law here by which we can multiply lambda times A and mu times A and then add them to each other afterwards. We have another interesting law that describes how scalar multiplication and multiplication of real numbers interact with each other. Notice that this product, lambda times mu over here, is a product of real numbers, whereas this product right there, that's a scalar multiplication. So on the left-hand side, you have one multiplication of 2 real numbers and one scalar multiplication, whereas on the right-hand side of the equation, this product is a scalar multiplication, and this product is also a scalar multiplication because mu times A is a matrix. And finally, we can add the 0 matrix to the matrix A, and that does absolutely nothing, so the 0 matrix is the neutral element with respect to addition. Recall that the 0 matrix is simply a matrix made up of all zeros of the correct size. The notation does not indicate the size of the 0 matrix, and so we just assume it's of the same size as the matrix A.